Okay, thanks so much. Yes, I'm going to talk about some big questions. Mars, life on Mars, water on Mars. And I'm also going to talk about Rosalind Franklin, which is the ExoMars rover. So you've got these. There'll be some half a dozen times when you need these. I've got a little symbol, so it should be obvious when to put them on and when to take them off. All right, so just better pick this up. So I'm going to start with a video, and I want to show this video, which, I hope works. Never work with children or animals or use videos on PowerPoint. So this is the Mars Science Laboratory. It was a NASA mission. It was launched in 2012. Those people there, they were not just the people working on it, they were the people just there to support. The launch is a very risky time. It could all just, explode. These things happen. What we're seeing now is animation, and it's showing the rover on its way to Mars. It takes 6 to 9 months to get to Mars. When you get to Mars, obviously you're going very fast, you have to slow down. Now Mars is good here because Mars has an atmosphere, so that helps us slow down the ship as it's on its way down. You can also use parachutes, which is another old-fashioned technology, good for slowing down in planets with atmospheres. But here's even better technology. This is actually what happened. It dropped the thing out the bottom, and it flew down, the rover held in this cradle, and then amazingly, it was released on these cables down to the ground where it essentially was ready to go the moment it landed. This thing's called a sky crane, and it flew off, crash landed somewhere else, and here's the rover now on the ground, ready to go. When we first heard about this, I couldn't believe they were going to do this, frankly. I just thought it sounded too much like science fiction or engineering fiction, but it worked perfectly, and they're actually going to use this same system on the next Mars rover. So this rover, I just want to give a sense of the scale of doing this. Enormously expensive, $2.5 billion, hundreds if not thousands of people, and some of the most talented engineers and scientists in the world spent many, many years building it. It's as big as a car, as you can hopefully see here. This is it before it launched. It's nuclear powered. It's uses radioactive isotope decay to generate electricity. There's controversy there, and so you have to be politically strong if that's what you say you're going to do. It contains a really impressive laboratory crunched up into a small space, fits into the boot of a Mini, a mass spec, a gas chromatograph, X-ray diffraction, and many, many more. And why is it doing that? Well, it's going to Mars to search for evidence of habitability. Could something live on Mars? And it's also going to examine the role of water. So actually, that was a huge investment, but the huge investment continues. So over the past decade or two, we've been moving towards 2020. 2020 is a really big year for Mars exploration. And again, we're concentrating on water. Now, NASA has this rover here, looks very similar. This is the NASA Mars 2020 rover. It doesn't have a full onboard laboratory. Instead, it's got a system to cache samples. It's going to drill a small distance into the surface, store these samples in safe containers, and going to leave them to be collected by a later rover. This is the first step in the International Mars Sample Return program. Now, that's a pretty good unique selling point. ExoMars rover, Rosalind Franklin, she's got a unique selling point as well. And, excuse me, and that is the deep drill. It can drill down to about 2 meters depth, and nothing else has ever done that before. At most, we scratch the surface. But then, just to up the ante a bit more, NASA have got a mini helicopter. So, they're always going to be one up, but hey-ho. Okay, so I've said we go to Mars, we spend a huge amount of resources on it, and I can hear people saying, oh, well, so what? Why do we care? Well, I would argue that the reason we care is to do with life. Now, actually, the origin of life is a big thing, and it's really hard to study on Earth. We don't have many ancient rocks from the period when life was getting going on Earth. However, Mars has more ancient rocks exposed and is broadly Earth-like. So it's a planet where we could look for past or present life to compare with Earth. So up here we have a meteorite. It's called Allen Hills 84001. It was found, as the name suggests, in 1984. And when it was analysed in the mid-90s, structures like this were discovered. And it was thought that these were microscopic traces of life. Now, this was announced. Even the President of the United States of America made this announcement. Since then, scientists have rowed back from this. The community feel that whilst this is a possibility, it isn't necessarily true. There's abiotic ways to make all the evidence, all the lines of evidence that we use to say that we found life. But irrespective of that, I think that if we discovered life on Mars, this would be a big thing. It doesn't matter what culture you're from, what religion you follow. The fact that if you found life on Mars and it was independent from Earth, the chance of those two planets being the two planets in the solar system where life got going for no apparent reason other than they were next to each other, that seems almost impossible. So to my mind, that means that actually this would mean we would be finding evidence for life throughout the galaxy. And that, I think, I hope most people agree, that's a big thing. You know, that's a big cultural step for a society to make. So this is why we follow the water, because water is essentially what we need for life to thrive. A little bit about Mars now, for those who may not have done what I've done, which is spend the last 20 years looking at it. It's the fourth planet from the sun. It's very cold. Actually, the surface can get up to about 20 to 30 degrees C in a very small skin, certain places during the local summer. It's got an atmosphere, but it's very thin again, 200 times thinner than Earth's, and yet we can still have winds on Mars that blow sand around. We can form huge dunes and ripples. Mary Burke, who's sitting in the middle there from Trinity, knows all about this. She's written many papers about Martian sand dunes. There's a third of the gravity. We know it's got lots of big geology, famous things like Valles Marineris, a huge canyon system, Olympus Mons, a huge volcano. You know, these are all found on Mars. And it's the best explored planet after Earth in the solar system. But this isn't how I see Mars. It's a lovely picture, but this is what you would see if you were traveling there. But I see Mars, pressing the wrong button, more like this. So this is an elevation map of the Martian surface. The warm colors, red, are high. The cool colors, like blue, are low. The very highest points are white. And what you could just about see is that the difference between the north, which is very low, and the south, which is very high, is about 8 kilometers. That's a huge difference, you know, in regional topography. And you can also see that the south has got lots of these little round structures in there, impact craters. And there's a lot more of those in the south than there are in the north. Now that ties into the age of different terrains on Mars. Just like on Earth, where you have the Archean and the Cambrian, etc., we have different geological periods on Mars. So there's the Noachian, which is the oldest one, Hesperian, that's sort of the middle one. And then the Amazonian. The Amazonian is interesting because it essentially represents 3 billion years. And the feeling is that Mars, how it is today, pretty much it was the same all the way back through the Amazonian. Very cold, very dry. Now you can see how the distribution of these different, of the different terrain types that have these ages is very, very non-homogeneous. So in the north, it's all the young stuff, and in the south, it's all the old stuff, all the Noachian terrains. Now, on Earth, earliest life got going, well, there's obviously a lot of uncertainty about this, but 3.5 to 4 billion years ago. So it is that Noachian period, perhaps extending into the Hesperian, that is the period we're interested in if we want to go and look for life. Now, that's also good because what we know is that the Noachian was wetter than present-day Mars. There's a load of lines of evidence for this, but I'm going to just talk about a couple. So the first are what we call valley networks. Here's some examples. On the left here, you can see sort of branching contributory networks flowing downhill and debouching into this large basin, which is almost certainly an impact crater. It's probably been filled in by later stuff. These can be hundreds of meters deep. They can be a few kilometers wide, can be hundreds of kilometers long. They form integrated networks across much of the southern highlands. Here's another good example here. This is a very complicated one with lots of smaller channels feeding into large channels that all make their way into the main channel down here. It's just what you'd expect if you were to look at the Earth in somewhere arid where there was a bit of rain around as well. Another example, this goes completely the other scale. So we're not looking from satellites. This is one of the first really big science discoveries that the Mars Curiosity rover made. Actually, they drove past this rock, and it was only later when they looked at the images that they realized what they'd found. So here is the Martian rock, and what it is it's a load of pebbles stuck together in a finer matrix, and these pebbles are rounded, and there can really be only one explanation for this. It's a fluvial conglomerate. It's a rock that's laid down due to running water. It's a real smoking gun. And I think if you took these two images and didn't put the labels on it, wouldn't be that easy to tell which was Mars and which was Earth. And that made science in 2013. So that was a big thing. So we think Mars was wetter. However, there's a problem. The geologists look at the evidence and they say there's evidence for liquid water. But climate models find it really hard when they go back to try to model the Noachian climate of Mars to come up with any way to make a climate that would support this type of fluvial activity. For a start, the sun was fainter at that time. It's called the faint young sun paradox. So they had to look for other processes that could help warm the climate. So they've tried a thicker atmosphere. No, that doesn't work. It sort of freezes out and it collapses on the surface. They've tried adding extra types of clouds. No, that doesn't work either. It starts to work, but then too many cools the surface. Adding greenhouse gases of all different types, but they don't really persist. They don't create a long enough warm climate. So here's the thing. The conundrum is maybe Mars wasn't actually warm and wet after all. Maybe it was only wet very briefly. And so there's a competing hypothesis. There's what's called the icy highlands hypothesis, where basically Mars is covered in ice, and then occasionally water sort of leaks out of these ice caps and does the geomorphic work that we see now. Or there's the warm-wet version. It doesn't have to be very warm, but it is quite wet. So what I do is I tend to look down using remote sensing satellite images of Mars. And I've spent the last 15 years or so working on very recent, very young bits of evidence for liquid water with Coleman, who's been my collaborator for 15 years, something like that. We've published loads of papers about small amounts of liquid water on present day or recent Mars. But over the last 5 years, I've done more stuff on Noachian Mars, and this has all been led to via my interest in trying to work out where to land the ExoMars rover, which I've been quite heavily involved in. So what I do is I try to understand geology using remote sensing images. Now, Mars is a great place if you're that sort of person. It has amazing data and really interesting geology. I would argue that Mars has the same range of geological processes that we see on Earth, bar perhaps plate tectonics, and it's got some extra ones that we don't have as well. And on top of that, it's got amazing remote sensing data available. Amazing high-res images. This is about the best you get. This is called HiRISE. It's a NASA product, 25 centimeters per pixel. 25 centimeters per pixel on the surface of Mars. I like to say that you could spot a car on the surface of Mars, and not only that, you could probably tell what brand it is. So it's an amazing camera. Oh, and it can also make stereo 3D models as well. Now, if you've got bright eyes here, you might be able to see some strange streaks going down here and something down there. Well, that is the Mars Science Laboratory rover as imaged by HiRISE. And so you can see both tracks that it leaves behind, and you can even see those up there. So it's really an amazing camera, and we're very lucky to be able to do this. So I'm going to show two examples of my recent research. If you have a look on this, you'll see which color to put on which eye. If it doesn't work, try swapping them around. Some people's brains are just wired up differently. If you can't see it at all, you can either take them off, or better is just to cover up the red one and just look through the blue one, because then you won't get the ghosting. So I think there are more scattered around if people don't have them. So I'm going to finish off by talking about ExoMars, and I'm going to show these first. So don't put them on yet, because I haven't shown the, sorry, terribly sorry. So the first thing I'm going to talk about is Aram Dorsum. So this is some work I did when I proposed this as a landing site for the ExoMars Rosalind Franklin rover. What you can see is it's a flat top ridge, extends about 90 kilometers, appears to be set in some smoother, darker terrain. Sometimes there are multiple threads of this, other times it's sinuous and single-threaded. And so I'm going to talk about the work that we did on that. Now you can put your glasses on, I think, because there should be a... Oh, sorry, beg pardon. I'm going to look at these 3 areas here with glasses, and number 4 will be without glasses. So if you put your glasses on now, I have to do this as well, or I won't be able to see what I'm doing. So this is just an overview, and the point I want to show here is hopefully you can really see that these are ridges. These are flat top ridges, they're not channels. And hopefully you'll also be able to see that there are these big lumps of stuff sticking up all over the surrounding. These are outliers of material that was previously more extensive and has been eroded back. And some of them are actually right on top of the Aram Dorsum system itself. You should also be able to see a subsidiary ridge coming down here. It's a bit discontinuous, but there's actually quite a number in this area that form a contributory network for coming into Aram Dorsum. So here's the next one. This is just a typical bit of this Aram Dorsum ridge. What you can see here is again how flat this top surface is. There appears to be a sort of a resistant layer at the top that's preventing the whole thing from falling to pieces. And you should just be able to pick out some layering in the flanks. Here is this darker material that surrounds it. And one final thing to note is that an impact crater that's landed in the top of Aram Dorsum has produced blocks, it's produced boulders. So this impact crater has not landed into something poorly consolidated, it's excavating a rock. So, that tells us something about the lithology. Here's the next example, and here's where branches in Aram Dorsum join. So here's one branch going along here. And what I hope you can see here is the branches appear to be true junctions. They're actually meeting at the same level, same height. There's another one down here. This one appears to have some subtle levees or ridges at the end. And down the middle of this one, there's a subtle, sort of slightly higher step across the middle. Here's another one of these outliers. As a rule of thumb, I normally stretch the vertical by about a factor of 2. It just makes it, step out a little more. So, but it doesn't alter the science that we're talking about. Here's a final one, actually second to final one. So we're now looking down on top of Aram Dorsum. And what I hope you can see is there's this central ridge here, but there's also another platform down here, which is also very flat. So it's almost like you have 2 flat top ridges, one on top of the other. Now at the back here, there's a bit more structure. So I'm now going to show an image looking at the back section. So here, what I hope you can see is this is the sort of the topmost resistant ridge, part of the ridge, but there's other small horizons where it appears to be more resistant material, forming within this ridge. So the ridge isn't just a simple structure with a resistant layer on top and weaker layer underneath that's been eroded. There's multiple generations of resistant materials. So if you take your glasses off, because I'm afraid I couldn't find a good anaglyph for this one. So if you remember, I said some of these ridges join at true junctions. Well, this is a counterexample, whereas this branch here, A, appears to be overlying C and possibly also B. And then up here where you have this little arrow, there's a faint trace of a ridge system that appears to be buried within this smooth, dark material that surrounds these ridges. So that just summarizes some of the observations that I've shown you. So here's our analogues. This is in Utah. And what this is an inverted fluvial channel. If you go into the field, which we did last year, it's about 15 meters across. It's got a layer of resistant sandstone at the top, well cemented. It's got some conglomerate bits in. It's full of cross-bedded sandstones with quite large bits in. It can only be fluvial. So this was once the bottom of a river. Okay, but it's now a ridge. Now all around here is less resistant material. It's mainly mudstones, siltstones. It's got some lenses of fine sediments in. And actually, when you go and see the bigger versions of this, which are nearby, there are whole other layers of resistant, thick sandstones within the body of these channels. So our interpretation, we're not the first person to make this, of course, is this is the channel body, and this is the overbank deposits, or the floodplains, if you want to call it that. And what has happened here is over time, the channel has migrated or has avulsed, it has moved to a different position, it's built up floodplains around it, and the whole system is essentially growing upwards, leaving these ribbon-like bodies of sandstone set within finer grained materials. Then what's happened, it's been buried, and then erosion has happened, and the bit that remains upstanding is the sandstone body rather than the finer material around. And so this is what we think Aram Dorsum is. It's a fluvial channel. So it tells us quite a lot of interesting stuff about that part of Mars. Now the real killer is this. So this is Aram Dorsum here. This is some work that my PhD student Joel Davis did, following on from my work on Aram. And so I set him to looking for more of these things around this area of Mars, which is called Arabia Terra. Blue were the erosional fluvial valleys that I talked about right at the beginning, which everyone knows about, but this was a huge gap. Everyone thought that this part of Arabia Terra didn't have any evidence for fluvial channels. Turns out it has got huge amounts of evidence. It's just they are aggradational systems instead of erosional systems. So that's really a really key result, and that was published in Geology a couple of years ago. So Aram Dorsum, it was once a river. It's aggradational, not erosional. And to have a system like this, you need a long supply of water and sediment. You need to redistribute and move the sediment. When we actually measured the volume of Aram Dorsum, we've worked out that similar sized systems on Earth normally take many hundreds of thousands to millions to tens of millions of years to form. So they cannot form in short periods of wet activity. Looking at the local stratigraphy, it puts it sweetly into the Noachian part of Mars's history, and in fact it's in the mid-Noachian, so it's really quite old. And one of many systems in this region, all of the same sort of age, so this probably requires a wetter climate than is proposed. I'm going to very briefly talk about one other bit of work. This was also a landing site proposed to ExoMars. This is called the Hypanis Delta. So this was 2,000 kilometers further to the west of Aram. And what I hope you can see is down here there's a small fluvial channel, an erosional channel. And then at this point where there's actually a break in slope, there's a big sediment fan here. Well, this is what happens on Earth. When you have a river debouching into the sea or a lake or even into a flat-lying plain, all that sediment is deposited. The water no longer has the capacity to carry the sediment. This one is particularly interesting because it's not just a simple fan. There's actually protuberances like this, which is actually an inverted fluvial channel, and then extra lobes. And further down here, there's a whole other system again. So this one is superposed by this one, and this one leads out here to another fan. So that's really, really interesting. We're going to go back on the glasses now, just to show what this one looks like. So this is now looking back at it, and the point I want to make out here is, well, first I want to apologise for this one, which didn't blend properly. I don't know what happened there. But the point I want to point out is how incredibly flat this is. This is a really flat system. So again, that matches what you might expect if this was a delta instead of an alluvial fan. And then down here, if you follow this channel, you can see these little, we call them mesas or knobs of material. And again, these are outliers from a layer that was previously covering everything that has been eroded back. And so this shows that this is ancient and it has been protected from the Martian environment for a long time by burial. So if we have those off then. So the thing about Hypanis is it's actually enormous. It's the biggest delta system on Mars. It's got a huge catchment, which you can see here. So this is the delta up here. This is the catchment. This is Vallis Marineris, by the way. Aram is down here somewhere. And the fact that you've got these lobes that persist out into the basin, this suggests that the delta stepped out into the basin. The thing that only could allow that to happen is if the base level was dropping, if the level of fill in a standing body of water was dropping downwards. Furthermore, when you plot out the topography, there doesn't appear to be a bound downstream. So that standing body of water could have, in fact, have occupied the whole of the northern plains of Mars. It could have been an ocean. Now, again, we're not the first people to say that, but it's another bit of evidence pointing to the fact that that ocean may have existed. And it's at the Noachian-Hesperian boundary, which is, again, the sweet spot for looking for life. So just to summarize those bits of work is, they're both fluvial landforms, very different. Aram Dorsum and all its brother and sister channels, they need a lot of water and a lot of time to form. Now, Hypanis itself, we don't know how long it took to form, but we do know that it must have formed into a very large body of standing water. And so I say, with just these two observations, I think both provide a real challenge to the idea of modelling Mars's Noachian climate as icy highlands that are very briefly punctuated. So to me, this adds to the Mars was warmer and wetter debate, and I just think the climate modelers need to go out there and do their job a bit better. But I'm hoping there's none here. So, and again, it reinforces ancient Mars's habitability credentials. All right, so now I'm going to talk about Rosalind Franklin, the ExoMars rover. So it's an ESA mission. It's going to be launched in 2020. It's going to land in 2021. And it is unashamedly about finding life. We've skirted around this for 20 years, but ESA have said, you know what, blow it. We're going to go and we're going to do our best to find life. It's a bold thing to do, which is rare for ESA, I think. So first of all, you need a decent landing site. You've got to have somewhere that's in that Noachian sweet spot, and it's got to have strong evidence for past liquid water. Now, my involvement was, to begin with looking for landing sites. That's what I do. I look at remote sensing data, but I also do quite a lot of field work to try to support my remote sensing work. It's nice to know all these different landscapes and landforms before you try to see them on other planets. And so I got involved in the Pan-Cam. This is the eyes of the rover, the Pan-Cam instrument team. Now, this is a multi-spectral camera. It's got stereo. It's got a built-in high-resolution channel as well. So this is going to be an incredibly useful tool for doing physical geography. It's going to help us be the hand lens and binoculars and eyes of a geologist on the ground, because we need to do the geology before we can do the astrobiology. So I'm currently the deputy science lead of Pan-Cam, and I've led rover field trials where I've been trying to test how we're going to operate the whole of the ExoMars rover in the field. We went to the Atacama, we went to Spain, went to Utah, where those images were from. So my involvement has really moved from being involved in just looking at remote sensing pictures to being thoroughly involved in trying to make the best possible processes for a rover geologist with these instruments be able to give us the best possible information so we can drill in the right place. For me, that's what it's all about. So I've said it will search for life. What's it going to look for? Well, it's going to look for biosignatures. Now, that's a big catch-all thing. Again, I'm not an astrobiologist, but what I understand is there's two types. There's the unlikely, which is the morphological ones. So we might be seeing decameter to meter scale structures of some kind of microbial mats or other things like this. But we've also got an instrument called CLUPI, the close-up imager, that might be able to pick out microscopic traces of structure that maybe give a hint that they were formed by life. I think it's more likely that if we'll have success, we will find chemical biosignatures, leftover organic carbon molecules, chain molecules. Maybe they'll be split up into lengths that are of, that have repeated patterns or repeated structures that might tell us something about, biotically produced chemistry. How will it do it? So it's got this amazing onboard laboratory. I won't go into too much detail. You can see these are some of the pieces that all fit together into what's called the analytical laboratory drawer. But it's got a laser desorption mass spectrometer and a gas chromatograph. It's got a Raman spectrometer. So the first one is really for looking at chemicals and isotopes. The second is mainly for mineralogy, but can do other things as well. And a visible infrared and reflectance spectrometer, which again is looking for certain types of mineralogy. But the thing that's really baffling is just how much other stuff you need, because you've got this deep drill that will bring up a sample. It's going to put it into a little hand that retracts into the rover, and then all sorts of crazy things happen. There are crushing systems, there are dosing stations, there's a carousel that moves the samples around. These things are moved within this rover on almost like conveyor belts. It's like a mini factory. And I think the engineers who built this should be, they should be knighted, frankly, because that's some amazing work. This is just an example of actually what it looks like. Up here, this is the holding stuff. I'm pretty sure this large wheel isn't involved with it, nor are these cable ties. But this shows, you never know though with space technology. There are space-rated cable ties. All of this stuff here will be going into the center of the rover. And in fact, that was done just a month ago. And the whole rover is now complete and is being integrated and tested in Toulouse. So we have a complete rover. So it's starting to feel really real. Now, there are some criteria that ExoMars might have to meet to claim mission success. So I would say that one thing we know is that the Martian surface is really harsh. It gets battered with radiation. It's really cold. It's really dry. And several people have done some really good computer models to understand the radiation dosage at different depths for different types of materials. And basically, they came up with this 2-meter depth threshold. If you can get below that, then you'll be able to get biosignatures that haven't been destroyed or modified too much by radiation. At least that's the plan. So prior to drilling, you've got to find the best possible site, and that happens at 2 levels. One, it's choosing the right site, the right area of Mars to land on, and the other is when you've landed somewhere, is allowing your geologists on the team to guide you to the best possible place. Drilling is really complicated. It takes a lot of time. It's got a lot of risk involved. Everything you do on a rover mission has a risk tally. So we want to be minimizing the risk, minimizing the power, minimizing the time. So we want to make sure we put it in the right place. And Noachian age seems obvious, and the targets that we're probably going to get to want to get to are clay-rich. These have probably been altered, basalts, water has flowed through them, converted them into various clay minerals, which are both provide a good environment for life to get going, and also a good way of preserving life and biosignatures as those clays form. So this is how we did it. So this is the landing site selection. So you can see Aram Dorsum and Hypanis. Those are the 2 that I was involved in. We had 8 to 10 sites. Then there was a great big meeting in 2015, and we agreed that we would down select to 4. And then every year we had a bake-off or strictly style elimination, where you have a big presentation, everyone does their best, and then a panel of judges rejects one. So my one, Aram Dorsum, made it to the semi-final, so I was kicked out 3rd. It was very sad. And the final 2 were Morth, which is up here, and Oxia Planum, which is down here. Morth has been studied a lot. Everyone knows about its thick clay and clay sequences, and a lot of different papers have been written about it. And yet it's never managed to be at the top of the list for a landing site. Oxia has arguably a less diverse amount of clay, a series of clays, but the reason it was chosen was it's an easier landing site. There's more chance when you gather the science and the engineering and risk together, there's more chance of a successful mission at Oxia than there was at Morth. So that's why it was chosen. So again, this is the Morth site, just to give some context. It's in a relatively uninteresting sort of part of Mars. But then you zoom in here, and I'm going to explain this. So these are individual high-rise images. Each of these is 25 centimeters per pixel, 5 to 10,000 pixels across, 5 to 10,000, maybe 30 or 50,000 pixels long. And that's each of these. This is a vast amount of data that's being collected. And it also requires a vast amount of time to analyze. So we can't do that. We can't analyze this whole data. So our preliminary landing uncertainty area was all around here. So recently, ESA have produced these 2 landing ellipses. So they think that this one, if we launch in July next year at the beginning of the launch window, so as soon as we possibly can, the Russians say, launch window open, and we launch, we will land here. We have a 2/3 chance of landing in here. There's another chance of landing a bit further down. If it's rainy or if there's some other problem, we won't be able to land at the beginning of the launch, at the beginning of the window, only at the end, in which case we will land here. Slightly larger area of uncertainty. The main features in the landing site at this scale are these fluvial channels, erosional channels coming in here. There's a big fan system here. There's another channel system going out here. And the really interesting things, which you don't really know what they are, lots of the local topographic lows are filled in with these darker, more rugged surfaces. There's a lot of these around. You see them like this. And some of them appear to have formed within craters. Some have formed in craters which have then been eroded away, leaving them upstanding as little pancakes. But the rest of it is all quite, pretty much the same. It's low albedo, relatively smooth, and covered in sort of small fractures. If we're going to put the glasses on again. Now, as soon as everyone's got all the glasses on, I forgot I was going to take a picture of everyone with their glasses on. So I don't know how good they are. So if everyone looks interested, or as interested as they can be. Thank you. There we go. That's the only reason I do this, really. So what we have here, oops, better move on. So this is the fan system. So this is the fluvial channel coming in here. It's a bit more messy than Hypanis. You can't see it so well, but what you should be able to see is there's a sort of a fork shape coming out here, another one coming out here, and here's a main fan in the middle. It isn't so clear here that you have additional fans at the edge of these channelized branches, which was the evidence that was used in Hypanis to say this is a delta as opposed to an alluvial fan. So we're not sure whether this is an alluvial fan or a delta. The site proposer, Cathy Quentin, she's very convinced that it's a delta, but I think she's open to the fact that we just don't know at the moment. I'm going to move on then. This is a bit of a, it's not easy to see everything here, so let me explain it. So this is one of these dark, rugged regional areas. You see it's slightly upstanding, and there's a transitional area coming down here. It's almost like a skirt around it of quite rugged stuff. But then by the time you come out into these areas, these are brighter materials. You can see there's some undulations. There's also these little patches here of transverse aeolian ridges, which are a type of large ripple-like form, maybe a metre or two high, maybe 20 metres across, hundreds of metres. And this is something that we see all across Mars. And the name transverse aeolian ridge was actually coined by Mary Burke, who is actually sat down there. So thanks, Mary, for... We now just call them TARs instead of transverse aeolian ridges. We don't want to get stuck in one of these. If you get stuck in one of these, you're almost never going to get out. Right, so those probably come off. Now, the thing that makes this site interesting really isn't the geomorphology, it isn't the fan, it isn't these dark capping units. The thing that makes it interesting is it's full of clays. So the remote spectrometry instruments and the spectrometry people, they have analysed this area to death and they've produced these maps. So red is where the iron and magnesium-rich clays are. The blue dots, these are a lot more speculative observations, but these are finding a more diverse range of clay mineralogies. So aluminium and rich are also involved. They found some opaline signals actually in the delta. And basically all those dark resistant outliers, these have mineralogy that makes us think they're volcanic minerals. So they're not clay minerals at all. So that leads to what is our current understanding of Oxia Planum's evolution, how it got to be the way it is. So we think that to begin with, started as most of Mars did, a mixture of impact, ejecta, volcanic products, sediments of all types, maybe aeolian, maybe some fluvial. But what we think happened here specifically is there was groundwater altering this basaltic material to very early on in Mars's history to make this red layer, which are the clays. Then later on, oh, sorry, I'm pressing the wrong button. Later on, during the Noachian Hesperian boundary, river systems came in from the east and they produced this fan system. They almost certainly produced other sediments down into the basin, and that would especially be true if this were a delta and not an alluvial fan. Now, interestingly, this is at exactly the same elevation as the Hypanis Delta that we saw just a few slides ago. And so that raises the, it might be a coincidence, but potentially these were both deposited into a standing body of water that had the same equipotential surface at the same time. So we might be seeing, again, more evidence of oceans. So looking for evidence of oceanic material here is a primary task of the geologist on ExoMars. When all this had stopped and Mars had dried out, we come to the early Amazonian, and these dark resistant materials were overlaid across much of the landing site. The working hypothesis is that these were lava flows, but I think there could be many other processes. They could be pyroclastic, so rather than effusive. They could be explosive volcanic products. They could be other things. When we went to places in Gale Crater where they had similar capping units, lots of people thought they were going to be lavas. Turned out they were Aeolian sandstones, thick Aeolian sandstones. So we just don't know. But we will go when we get there and have a look with the ExoMars rover. Then finally, wind erosion has created the landscape you can see today. It's, all of these, this large dark unit has been eroded back and to reveal the clays underneath. And that's really good, because that means that not only have these clays been buried to a certain level and protected from the Martian environment naturally, they've also had a lovely cap of basalt, or whatever the material is, over the top of them for about 3 billion years. So they're going to be really well preserved. This is just the right place to drill and find these materials. You would probably argue that if you went as close as possible to one of these capping unit areas that was probably the most recently exposed, that would be the place to go. So, right, coming towards the end now. So this is ExoMars' plan of action. It's going to launch in March 2021. This is going to be stressful for everyone on the mission. I've only been on the mission for about 5 or 6 years. I'm already crossing my fingers. People who've been on this mission for 15 years, it must be terribly terrifying, because obviously things go wrong on launches. So fingers crossed that doesn't. Then you've got landing, which is even more terrifying, but we're just going to assume that's going to work, because what else can you do? When it lands, it has about 30 sols where it commissions the rover. It has to go off the landing platform because it doesn't have the sky crane. It has to land on a platform, move down some ramps. About 30 days after that, we begin the mission. And so the first thing we need to do is, are we on the clay-bearing unit? And we hope we will be, because there's something like a 80% chance that we will be. And then we need to start to understand those materials. What are they? How were they laid down? How were the clays created? And what was the history of water-rock interaction? So there's got a lot of geology to be done before we even begin to get our sample and then ingest it. And that's where, in a sense, the first stage of the mission finishes. And the next step, the real mission success step, and that is for the teams who are working on these analytical laboratory draw instruments to do their thing and make up their minds and say, do we have life or signs of past life or not? The way they're going to do that is quite complicated. There's a huge scoring system. We will never rely on just one piece of evidence. It's going to have to be a series of consilient observations with all the different instruments that will be put together to form the ExoMars life detection score. So that's now the thing that we're working on. So thanks very much. This is another nice view of Oxia, and hopefully you can see that that's the rover to scale in this landscape. So if it all lands safely, then hopefully I'll have more things to say in 2021. So thanks very much.